A very good morning to all of you. Today we are going to discuss part 2 topics of week 2. So we have already discussed AI problems in the previous class. Now we are moving to production systems. So what is a production system? A production system is a fundamental way of representing knowledge and performing reasoning in AI. Production systems provide appropriate structure for performing and describing such processes. Say production system is a way to store knowledge using rules, reason and solve problems, and simulate human decision making. In AI, it is commonly used in expert system, game playing, and problem solving programs. So we can say that a production system should think like that. If this situation occurs, then do this action. A production system has four main components. We will discuss one by one. First one is a set of production rules. So what are production rules? Rules we can written like that. If a particular condition, then corresponding action. So that means the structure of the rules will be there is a left hand side and right hand side. Left hand side means condition that must be true for a rule to apply, and right hand side means action performed when the rule fires. For example, we can say that if traffic light is red, then stop vehicle. So if then traffic light is red is the condition, and then corresponding action is stop vehicle. So rules represented the knowledge of the system. So we can simply say that rules represent the knowledge of the system. So a set of rules consisting of a left side that determines the applicability of the rule, and right side that describe the operation to be performed if the rule is applied. And the second component is a database that we can say that working memory, or we can call it as fact base. So what is a database? So database of current facts established during the process of inference. So that means it is store the current facts about the problem, represents the current state. For example, we can say that traffic light is equal to red, speed is equal to 40. So all this information we are storing in the database. So as rule fires, the database add new facts, remove the old facts, and also update the existing fact. And then the third component is control strategy. So control strategy that specifies the order in which the rules will be compared with the facts in the database, and also specifies how to resolve conflicts in selection of several rules or selection of more facts. So we can say that a control strategy decides which rule to apply next and in what order. That is the main thing. So control strategy means that decide which rule to apply next, and it determines the order of rule execution, and it also handles conflicts when more than one rule can be applied. For a particular case, for a particular state, more than one rule can be applied. So this control strategy will handle the conflict when more than one rule can be applied. So there are multiple rules may applicable at the same time. So common conflict resolution methods, we can say that rule priority and most specific rule first, and rule using latest facts, and first matched rule. So this components provides an intelligence to the system. And the next component is a ruling firing module. So this module actually execute the selected rule. So rule firing rule, we can say that executes the selected rule, performs the action on right hand side, and modifies the database. For example, we can say that when rule fires, then for example, we are already seen when traffic light is red, the action is stop vehicle. So we can say that when rule fires, vehicle stops, and accordingly the database will be updated. Now we will see how a production system works. So the first step is match. That means find the matching rule with the facts in the database. And then second step is select. So choose one rule using the control strategy. And the third step is fire. Execute the corresponding rule. And next step, update. So then modify the database accordingly. And last step is repeat. That means continue until the goal is reached. So next we will discuss about the problem characteristics in artificial intelligence. So what are problem characteristics? So problem characteristics that describe the nature of a problem that an AI system must solve. So they help us decide which problem solving method to use, which search strategy is suitable, how difficult the problem is. So in AI, understanding the problem is as important as solving it. So we will see the problem characteristics one by one. Decomposability of the problem into a set of independent smaller subproblems. Possibility of undergoing solution steps if they are found to be unwise. Predictability of the problem universe. Possibility of obtaining an obvious solution to a problem without comparison of all other possible solutions. Type of solution, whether it is a state or a path to the goal state. Role of knowledge in problem solving. Nature of solution process with or without interacting with the user. We will see one by one in detail. So first one, decomposability of the problem into independent subproblems. That means a problem is decomposable if it can be broken down into smaller subproblems. So that can be solved independently and then combined. For example, we can say that there are decomposable problems are there. So that means solving algebraic expressions, planning tasks. So in this example here, we can see that there is a algebraic expression. So we can divide it into subproblems and we can solve each problem independently and then finally we can combine. So decomposable problems can be solved easily. For example, non-decomposable problems, that is chess, tic-tac-toe, where each move affect the future choices. So we can say that decomposable problems are easier to solve, and in the case of non-decomposable problem that require search and reasoning. So next problem characteristics is possibility of undergoing solution steps. So can solution steps be ignored or undone? So it means determines whether actions taken during problem solving can be reversed if they turn out to be incorrect. So the problems are illustrated in the three important classes of problems. Here we can see ignorable, recoverable and irrecoverable. So ignorable means in which solution steps can be ignored. So only final result matters. Example is theorem proving, equation solving. And second type is recoverable, in which solution steps can be undone. The steps what we can done that we can undone. So example is 8 puzzle problem. Irrecoverable means in which solution steps cannot be undone. The example is chess. So the recover problem allow trial and error. Irrecoverable problem needs careful planning. So in this example, you can see 8 puzzle problem. So moves can be undone and backtracked. So this is a recoverable problem. Next problem characteristics is predictability of the problem universe. That indicates whether the outcome of an action is certain or uncertain. For example, you can see the 8 puzzle problem. Every time we make a move, we know exactly what will happen. So the outcome is the certain outcome. Then in the exam, if we are considering the example playing bridge, we cannot know exactly what all the cards are or what the other players will do on their turn. So that is uncertain outcome. So we can say that there are two types of problems, deterministic and non-deterministic. Deterministic means same action that always result in same result, same outcome. So the example is 8 puzzle problem. In the case of non-deterministic problem, the outcome is uncertain. The example is robot navigation. So deterministic problems are easier to model and non-deterministic problems need reasoning and that means sensing and replan. Is the universe predictable? So there are three types of problems we can consider. First one is certain outcome problems, where in certain outcome problems, result of every action is predictable. Same operator applied in same state always produce a same result. So there a complete plan can be generated before execution, and a plan is means a sequence of operations, and this plan is guaranteed to reach the goal if followed correctly. The example is 8 puzzle problem block world. And once the plan is created, no changes are needed during execution. And the second problem is uncertain outcome problems. In uncertain outcome problems, result of an action cannot be predicted with a certainty. So in this case, the planning approach is a generated plan cannot guarantee the success. It only has a high probability of reaching the goal. The planning must consider when possible failures occurs. Then example means robot navigation in real environment, medical diagnosis, autonomous driving. All these are examples of uncertain outcome problems. So the plan is tentative and not guaranteed. And the third case is plan revision using feedback. So in certain environment, plan are revised while being executed. So first execute the action, then observe the environment. So that means feedback is collected and check if expected outcome occurred, then modify the plan if necessary. So this is known as replanning or plan revision. The example is a robot avoids an unexpected obstacle. And another example is navigation system changes route due to traffic. So planning become an interleaved process. That means we can say that first plan, then act, then observe, then revise. Next problem characteristics is a good solution absolute or relative? In AI, does a problem have one fixed, absolutely correct answer, or does the quality of the solution depend on available knowledge, assumptions, or context? So we can say that whether there is a one fixed correct answer or the solution depends on available knowledge, assumptions, or context. So here we will see one example. So there is a list of facts. Each sentence we can call it as a fact. Shiva was a man. Shiva was a worker in a company. Shiva was born in 1905. All men are mortal. All workers in a factory died when there was an accident in 1952. No mortal lives longer than 100 years. So there is a list of facts are given, and we have a question. Is Shiva alive? So how we can solve it? So we will see the solution. Here we can see the two methods for solving this problem. So first method, we are considering some of the facts. Shiva was a man. Shiva was born in 1908. As per the knowledge base, all men are mortal. So that means Shiva is also a mortal. And now it is 2008. As per the textbook, it is 2008. So Shiva's age is 103 years. So that means now Shiva's age is 103 years, and it is given that no mortal lives longer than 100 years. So we know that Shiva is also a mortal. So Shiva is not alive. We can conclude that Shiva is not alive. And the second method, Shiva is a worker in the company, and it is given all workers in the company died in 1952. So that means Shiva is also died. So the answer is Shiva is not alive. So we can say that we can consider different facts and we can find the solution. Using the given facts, we are concluding that Shiva is not alive. So is this solution absolute? No, this solution is not absolute. So the conclusion depends entirely on the given knowledge. So you can say that in AI, a solution is absolute if it is true under all circumference. And a solution is relative if it is true only with respect to the given assumptions and facts. So now our next problem characteristics is the solution state or a path. So this problem characteristics help us decide what form the solution should taken in an AI problem. So there are two possible forms of solution. One is actually solution as a state. So that means only the final answer matters. We are not considering how we are reaching the solution. Intermediate reasoning steps are not required. and no need to record how the solution has reached. Only we are considering the final result. And the second one is solution as a path. There, the solution is a sequence of actions and steps, and each step is important and each path must be shown. We can see example, this example we are considering a natural language understanding. Here it is given a bank president ate a dish of pasta salad with the fork. So the sentence is ambiguous. You can see that here the goal is find a consistent interpretation of the sentence. This involves we have to decide, does bank means financial institution or river bank? Is dish the plate or the food? So next, does pasta salad contains pasta? Then does with the fork modify ate or pasta salad? And also what if with the vegetable is added? So here the final answer is a single correct interpretation, and the system only needs to output the final meaning. And the reasoning steps do not need to be stopped. So no recording of the processing is necessary. So here the conclusion of this problem, the solution is a state and not a path. So because only the final consistent interpretation matters here and no record of processing is required here. So for example, we can say that in the path-based problem, best example is puzzle solving, 8 puzzle problem, navigation, robot moving to a goal, and then game playing, that is chess moves. All the here the path movements are also important. The next example is water jug problem that we already discussed. That also here there also the path, each path also the path movement also required. So the path leads to the goals must be reported in this case. Next problem characteristics is what is the role of knowledge? So that determines how much domain specific knowledge is needed. There are two types, weak method and knowledge intensive. And weak method problem means only little knowledge is required. So, for example, example is maze. And another one is knowledge intensive. Knowledge intensive means users expert knowledge. The best example is medical diagnosis. So, knowledge based systems are faster and smarter, and weak methods are more general but slower. In the case of playing chess, knowledge is important only to constrain the search for a solution. Then, for reading a newspaper, knowledge is required and even to be able to recognize a solution. Next problem characteristics is next the task require human interaction. So that determines whether the system solves the problem autonomously or interact with the user. So there are two types of problem, non-interactive problem and interactive problem. So first one is non-interactive problem. The best example is solitary problem in which there is no intermediate communication and no demand for an explanation of the reasoning process. Chess program is also the example of a non-interactive problem. And next one is interactive problem, or we can say it as conversational problem, in which the intermediate communication is to provide either additional assistance to the computer or additional information to the user. So interactive systems need explanation capability, and in the case of non-interactive system that works independently. So we will see why these characteristics are important. So the production system are used to describe and control search in AI using rules, facts, and control strategies. We already discussed that. And studying these characteristics that will help us to understand how they behave and decide which production system suits which type of problem and also implement them effectively. So we can say that production system provides us with a good ways of describing the operation that can be performed in a search for a solution to a problem. So they do this using rules, facts, and control strategy. So there were two questions we can consider here. Can a production system be described by a set of characteristics? And how can they be easily implemented? And what relationship are there between the problem types and types of problem well suited for solving the problem? So next, we will see the classes of production system. So first one is monotonic production system. It's a production system in which application of a rule never prevents the later application of another rule that could also have been applied at the time the first rule was selected. That means once a rule fires, facts are never removed. The new facts can be added to the knowledge base. So knowledge base only grows. The best example is theorem proving mathematical reasoning. And this is simple but not suitable when facts may change. And the second case is non-monotonic production system, in one in which this is not true. So that means rules may add or remove facts. So knowledge base can change dynamically. The best example is game playing. So while playing the game, the knowledge base can be changed dynamically. And real world decision making is also an example of non-monotonic production system. This is more flexible and also more realistic. And the next is partially commutative production system. So it's a production system with the property has if a application of a particular sequence of rules transforms state P into state Q, then any combination of those rules that is allowable also transforms state P into state Q. So that means a sequence of rules that changes from a state P to state Q, then if we are changing the sequence of that rules also, it affects the system from state P to state Q. Then next is commutative production system. Commutative production system is a production system that is both monotonic and partially commutative. So that means the order of applying rules does not affect the final result. The best example is algebraic simplification. In the case of partially commutative production system, there, if you are changing the order also, if you are changing the order of rules we are applying also, it transforms state P into state Q. And the commutative production system is also working the same system. It also satisfies the properties of the partially commutative production system, and it is also monotonic production system. And we will see the four categories of production system. We will see the example theorem proving. It is an example of a partially commutative production system and also monotonic production system. If you are considering robot navigation system, it is partially commutative, but it is not monotonic. And chemical synthesis, it is non-partially commutative and monotonic. Bridge problem, that is non-partially commutative and not monotonic. Next, we will discuss issues in the design of search programs. So we know that search is a core activity in AI problem solving. Almost every AI problems can be viewed as search through a space of possible solutions. So we can see a search as a tree. So that means every search process we can be considered or represented as a tree. So root node we can consider as the initial state, and intermediate node we can consider it as the partial solution, and leaf node we can consider it as goal state or dead ends. So each edge corresponding to applying an operation or a rule. So hence designing a search problem is equivalent to deciding how to traverse this tree efficiently. And then next issue is actually how we will select the direction. So it can be a forward search or a backward search. In the case of forward search, we are starting from the initial stage. That we can consider it as a data-driven search, where applies rules and forward until we are applying rules forward and until we reach a goal stage. So forward search we are using when initial state is well defined and number of possible goals is spawned. The best examples are 8 puzzle problem, tic-tac-toe. And in the case of backward search, we are starting from the goal stage. It is called it as goal-driven search. And it works backward to reach the initial stage. And this is used when goal is clearly specified and only a few operations that leads to the goal. The best example is actually theorem proving. And next issue is actually rule matching. So at each node, the system must determine which rules are applicable. So in this rule matching process, we have to check the left hand side, that is rule condition, and also we have to check the current state facts. And efficiently we have to find the correct rule. So this is also a critical problem because poor matching may leads to a slow search, and in some cases many rules may be applicable in some cases. So the production system using a pattern matching algorithm. And next issue is actually representation of search nodes. So each node must represent current state, relevant facts, and in some cases history also. So simple problems, array or list are sufficient to represent the state. For example, tic-tac-toe problem game, that means game boards, array or list is enough to represent the problem. And in complex problems, you can use the knowledge representation methods like frames, semantic networks, and structured objects that we will discuss in the later modules. So this issue is actually known as knowledge representation problem. The next is actually choice of the data structure. So the data structure used that will affect the speed of operation, memory usage, and also the ease of rule matching. So problem types may be different types of problem we can consider. Games, their array representation we are using, and planning problem we can use predicate logic, and expert system we can use frames or rules. And we will discuss this predicate logic and frame and all we will discuss in coming modules. And then a good search problem that should balance the efficiency and expressiveness and also the scale. Okay, thank you.